In this final notes section, we look at implementing these equations in a software package to be able to get some results. And the engineer in us rejoices because this math has been fun, but we really need to have a practical outcome or else it's wasted time. We look at a commercial finite element method solver called COMSOL. This is driven by a graphical user interface, or GUI, that makes it relatively straightforward to implement and modify these model equations, which is really handy when you're performing research, as we do in our group, that's cutting edge, and we need to not only use the equations that are developed in this course, but some other equations that talk about some more advanced processes happening in the cell, such as degradation, for example. The cell schematic to keep in mind is the one that we've already seen, where the x equals 0 location corresponds to the current collector at the negative electrode side. X equals maximum value is at the positive current collector, and then I've got three regions: the negative region, separator region, and positive region. There's two coordinates in our model. One is the x coordinate, which is the spatial dimension, but then there's also a radial component within the particles inside of each electrode as well. We're going to go through our model equation by equation and show how to slightly rewrite the form of the equation to make it easily digestible by COMSOL, so I can easily enter it in a form that COMSOL will accept, and COMSOL will then simulate. The first equation that we want to implement is this one, the charge conservation in the solid. One thing that we have to discuss before going any further, though, is that in each region, it's actually possible to build a COMSOL model, like we've talked about, where this is x equals 0, x equals L neg, x equals L neg plus L sep, and x equals L total. I can build that geometry, define it, and then add the equations to this geometry and simulate it. However, if I decide to change one of the length variables in the equation, at least in present versions of COMSOL, I have to start over again at 0. I can't simply change L neg like I would like to do. It doesn't work. I have to delete my model, start over, and enter a new geometry, then enter all of the equations, and this is just a nightmare. That won't work. Instead, what we do is we define normalized coordinate systems. So the negative goes from x bar equals 0 to x bar equals 1. The separator also in COMSOL is going to go from x bar equals 1 to x bar equals 2, and then the positive up to x bar equals 3. So in COMSOL, it thinks that I've got a 3-meter wide cell, which I don't. So I need to adjust the equations to make the equations work with COMSOL's belief this is a 3-meter wide cell, and to provide the same answers as if it's, the cell of the actual dimension I want to simulate. So I desire to use this equation, but in fact, that's not really possible, or at least not practical. We're going to use a symbol x bar to represent position in our normalized length system, and x without the bar to denote the actual position. In the negative electrode, x bar equals x over L neg, gives me a 0, 1. And I guess the way I described, I would have to add 2 to this in the positive electrode. But what I've described here is x in the positive electrode going from 0 to 1 also. If I wanted to go from 2 to 3, I add 2. Thankfully, x doesn't ever appear as an absolute number in our equations. It occurs only as a derivative, and so any constant I add really doesn't matter because the derivative of a constant goes away. So generically, no matter how I describe it here, x bar is going to be x divided by the length of that region plus some constant. If that's true, then the partial derivative of anything with respect to x bar is something I can write using the chain rule as the partial derivative of that thing with respect to x times partial of x with respect to x bar. And if you look at this equation, x equals L times x bar, so partial of x with respect to x bar is simply L, and I can write the original partial derivative as L times the unscaled. So the scaled is equal to L times the unscaled. Or vice versa. If I start with a partial derivative of something with respect to x, I can write that as partial with respect to x bar times a scale factor, where this scale factor is 1 over L. So there's a symmetry back and forth. So if I'm using this normalized coordinate system, we recognize that gradient of some function when I'm using a 1D thing is equal to partial of m with respect to x. And if I'm doing a 1D thing, the divergence of m is also equal to the partial of m with respect to x. That's what I start with, but if I want to use our normalized system, I replace, everywhere I've got a partial with respect to x, I replace by 1 over L times partial with respect to x bar. I had a divergence operator there operating with x. Now I've got a divergence with respect to x bar with a 1 over L. Here I had a gradient with respect to x. Now I've got a gradient divided by L with respect to x bar. Those are how we change the model equations, and we're going to see this idea in all of the PDEs of the model. In principle, this is something I could enter into COMSOL and everything would work. However, COMSOL is trying to approximate all the basically 5 different equations. It's trying to approximate the Butler-Volmer and the phi s and the phi e and the CS and CE equations, all at every point in space, every point in time, trying to get the best approximation to those using its numeric methods. And if the equations are not all scaled more or less the same, so that the different sides of the right side and left side of the equation is more or less the same, then COMSOL ends up giving more emphasis to matching the big things than it does the small things. So the equations that produce big numbers rather than the equations that produce small numbers. So without changing the meaning of the equation, I multiply this side by L and I multiply that side by L, and this cancels, and I end up with something that works better in COMSOL for purely numeric reasons to enhance its ability to converge in the simulation. Now what I have is I have divergence of sigma effective divided by L times the gradient of this phi s equals as times f times j times L. And in COMSOL, there's an equation that implements something of this form, and this is how you would enter things into that equation. I would say, okay, the equation comes with this part built in, and I have to enter in the sigma effective divided by L, and I multiply by something called phi underscore sx. Now, in COMSOL, we're going to define a variable, as I show in this table, called phi s, which is phi s. COMSOL has a built-in notation that if I add an x after that, that means the derivative of that quantity with respect to x. If I add a t after it, it's the derivative with respect to time. So this gradient, is in fact that term. And then on the right-hand side, I have L times AS times F times J, where we define in the interface variables and typeset those in a fixed font and a Courier font to show these are what you actually type in COMSOL. So this is what we type, but in our equations, they look like this. Okay, we already said that. So that's equation number 1. I have to enter an equation. I have to say which parts of the geometry this works for. This, in fact, only works for the negative electrode and the positive. This does not operate on the separator region. I just have to tell COMSOL all of that. And equation number 1 is done. Equation number 2 is the hardest. We desire to implement the mass conservation in the solid, which is the only equation that uses the radial pseudo-dimension, r. I desire to implement that, but it doesn't use x, it uses r. And what it means is, at every x location in the cell, I am actually running an independent copy of this radial location to say what is happening inside of the radially symmetric particle that's at that location. So when I say the cell, I really mean at every x location in the negative electrode and every in the positive electrode. We don't have mass conservation in the separator region because there's no solid in the separator region. When we're working with this equation, we also normalize the radial dimension to define an r bar equals the radial dimension divided by the maximum radius, the radius of the particle, rs, which means then, because r squared shows up in the equation, r squared is r bar squared divided by rs squared. And that is backwards. It's r bar squared equals r squared divided by rs squared. And the partial derivative of something with respect to r also turns out to be 1 over rs times partial with respect to r bar. This allows us to rewrite our PDE. Change in concentration with respect to time is unchanged. But looking at the terms in the model, I have a 1 over r squared, which now becomes in r bar squared divided by rs squared. I have a partial with respect to r, which becomes 1 over rs times partial with respect to r bar. I have ds times r squared times partial with respect to r, so I've got ds times this times the partial with respect to r, also scaled. If I multiply both sides of this expression by r bar squared times rs and rearrange, I get what we actually implement in COMSOL. So multiplying by r bar squared times rs on this side and r bar squared times rs on that side, I have that rs squared and that rs squared cancel out. I have an rs squared in the denominator, which is going to cancel one of them, so I end up with 1 rs. I have an r bar squared inside of the derivative, which I can't pull outside because the derivative is with respect to it, so that stays. And I have a ds there as well. And this, multiplying that, goes there. And everything gets pulled over to one side, and I think everything works out in the end. So that's the idea. Now, COMSOL doesn't have the ability, as far as I know, to rename a coordinate in its model. So x is x and y is y. It doesn't have an r coordinate. So it uses in our model y instead of r. And it's going to then have y bar squared times rs times etc. everything else. Everywhere you see r bar, we use y bar instead. This picture visualizes how COMSOL implements the equations. So this is the x dimension of this cell. So this is the negative region, and this is the positive region. And this here is the r bar dimension, which is implemented as the y dimension of this cell. That means that this here is y bar equals 1, this is y bar equals 0, So this here is the surface of particles, and this is the center of particles. And if I take any slice in here, that describes what is happening within one particle at that X location. A different slice somewhere else is describing what's happening inside that particle at a different X location. And I've got diffusion happening only in this direction in the model. But at every point in the negative electrode, I have a particle, so that's why it looks continuous in the horizontal direction. Really, it's discretized in our understanding, but I've got a whole bunch of continuous particles here side by side, so that at every location there's essentially a particle. Same in the positive electrode. In this picture, red corresponds to high concentration and blue to low concentration. And this shows a simulation result where I started with a with an even high concentration in the negative electrode, so the cell was at high state of charge, and I started to discharge this cell. And what we're seeing is the negative electrode is preferentially discharged through the region closest to the separator, but there is some discharge happening everywhere because there is a color profile there, a color gradient. It's not uniform. Therefore, some lithium is coming out of every X location, but more is coming out of the X locations near the separator as I'm discharging the cell. In the positive electrode, the ratio of the conductivity of the electrolyte and the solid are different from the negative electrode, and so it operates a little differently. And in fact, almost all of the initial discharging of this cell contributes to changing concentration right near the separator, and very little gets here. So it's easier in this example for lithium to enter a particle and diffuse into a particle than it is for lithium to diffuse horizontally in the positive electrode, whereas in the negative electrode, the ratio is such that it's easier for lithium to go out this way. It's harder. It's easier for it to diffuse, and so the diffusion it's more uniform coming out of the solid and the negative electrode. So different properties affect the behaviors of the electrodes differently. If I had identical properties, we would see identical performances. I think we've said all of this. The vertical dimension is the radial dimension. R equals RS is at the top, and R equals 0 is at the bottom. The left block is negative electrode, right is positive, and we talked about the cell being discharging. To implement this in COMSOL, we've defined a 2D space for each electrode, and diffusion happens only in the so-called vertical direction and not in the radial direction, so we have to be careful how to implement our equations to enforce that to be true. It does happen in the radial, but not in the horizontal dimension. And in COMSOL, looking at the equation, this is really r squared, but it's r barred squared, but we enter it as y because COMSOL knows about y, it doesn't know about r. Times rs times the partial with respect to time, and then plus the divergence of, let's think about this in a second, something times the gradient of concentration equals 0. Well, when I'm looking at gradient of this two-dimensional region over here, that's partial with respect to x and partial with respect to y, or the radial dimension, as a vector quantity. And we said there is no diffusion in the x direction, so I have a matrix diffusivity element in there that multiplies all of the partials with respect to x by 0 and retains only the partial with respect to y in the outcome. And it enforces that the divergence is in fact 0 in the x dimension and only has a component in the y or r direction. And we define these constants as well. So those two require understanding some new ideas about implementing things in COMSOL. The remaining ones are just more of the same. In the electrolyte, I desire to implement this equation. This is a 1D x dimension model equation only. So this divergence becomes 1 over L times divergence when I scale it. This gradient becomes 1 over L times gradient when I scale it. This gradient becomes 1 over L when I scale it as well. So far, so good. Gradient of log CE causes us some problems because COMSOL does not have a form that can handle that directly. But we can write this differently. We can write this as gradient or partial of log CE with respect to x equals 1 over CE times partial of CE itself with respect to x. And that's how we actually enter it into COMSOL when we implement it. Again, we multiply both sides by L for better convergence. So the equation that we end up implementing is the divergence of kappa effective over L times the gradient of phi e, the derivative with respect to x, plus a kappa d factor, which is not written. Yes, it is written right in this equation. This, notice, because of the brackets, also is multiplied by kappa effective over L, so the over L is in that part. Times the 1 over CE times the CEX is the derivative of CE with respect to x again, and this is the right-hand side there. Kappa effective is kappa effective. Kappa d factor is kappa d divided by kappa effective. So this turns out to be a simple number, actually, where kappa effective is not so much. And then all of the other terms are listed as well. The last equation is, the last PDE anyway, is mass conservation in the electrolyte. This is the equation we want to implement. Once again, the normalize process gives us these 1 over L terms. And what we actually implement, multiplying both sides by L, is epsilon E times L times partial CE with respect to time, and bringing things over, plus the divergence of this term here equals this source term there. And we define these variables here. When we run COMSOL, we are presented with a graphical user interface. And this is something that's probably impossible to show on a static screen. So there's going to be another lecture video also, a section 12, that has no lecture notes correspondence, where I show you in a video actual demonstration of COMSOL running and how you start it and what your models look like inside of COMSOL. And I think that will be instructive. But this screen here at least gives you an idea before you see that video of what kinds of things you'll see. With this size of display, it's hard to see everything clearly, but there are some definitions over here of constants and functions that we need. There's a one-dimension model over here which talks about the partial differential equations that are implemented on the x dimension only. There's a two-dimensional model as well that talks about the equation of solid concentration. There are some regions over there that talk about simulation control. So all of this is where the parameters of the model are stored, and that's how you access them through that window. Through this pane here, if I click on some specific element, it will give me information on that element in the middle pane, and I can make some modifications, or I can see the values and so forth in that window. And then in the right, we can see some output graphs. And in this case, this is the output of a simulation where I had a cell that was rested for a while, then charged for a while, then rested, then discharged, and then finally rested again. And then there's some messages that we can see down there. So hard to explain with a static screen. Tune in to the next lecture video and we'll do a demonstration. This concludes the material for this chapter, and we're really making fantastic progress. We're now at a point where we can fairly readily simulate cell performance and look at a lot of aspects of its behavior. However, the equations of our model, they're simplified a lot versus Chapter 3. Might not look like it, but they are still too complicated to implement in a real-time embedded system, which is what we would need for a battery control example. So our next step, looking into Chapter 5 and 6, we look at ways to reduce the complexity of the model equations while still retaining all the physics. By the time we get to the end of Chapter 6, we've got a reduced order physics-based model of similar computational complexity to the Chapter 2 models. Took an awful lot of work to get there, but huge benefits derive from that as well. Lastly, as we did in Chapter 3, we have a glossary of terms, and this might be helpful to you. If you forget what a term is, you can just flip to the glossary and be reminded of that.